Good morning students, 12th standard physics lesson 3 magnetism. In this class we are going to discuss about toroid. So toroid is nothing but a solenoid is bent in such a way that two ends are joined together to form a closed ring shape. So consider is a solenoid with so many turns are wounded on the material. So if two ends of the solenoid are bent in such a way to make a circular ring, that is closed ring shape. So that is, this one is a solenoid. So this one is a solenoid, this one two both ends are connected to form like a ring, that is toroid. So we are going to find the magnetic field at three different points. So interior of the solenoid, exterior of the solenoid, and then inside the solenoid. So this is a picture, see this picture. So the two white round, that is a solenoid. The dot and plus represents the current going in and out. So like that, current going in and out. Then, so what is the magnetic field at the point P? That is interior of the solenoid. Then have a radius R1. Then exterior of the solenoid at the point Q, that is with the radius R3. Then inside the solenoid. So that white color chalk represents the solenoid. That radius R2. We are going to find what is the magnetic field present inside the solenoid. So first, so we are constructing a Amperian loop of L1. So that is have a radius R1. So it's a circle. So the circumference of the circle is formula 2 pi R1. So using Ampere circuital law, so closed integral B dot dl is equal to mu 0 I enclosed. So I enclosed in this loop, that is loop of radius R1, that is what is the current enclosed in the loop, that is equal to 0. So I enclosed equal to 0 means closed integral B dot dl is also equal to 0. So what is the magnetic field at the point P is 0. So the first loop over, that is interior of the toroid. Then exterior of the toroid. So exterior means outside. So what is the current? So loop L3 equal to 2 pi R3, it's a radius R3. So this one loop from center to at the point Q, there is a Amperian loop of radius R3, that is L3. So L3 is equal to 2 pi R3. Then using Ampere circuital law, closed integral B dot dl mu 0 I enclosed. Similar, then I enclosed. So what is the I? What is the current enclosed in this toroid? Just see. So current going in and out. So going in and out is represented by the dot and plus. So the current going in and out is cancelled. How? So each turn. So every turn current goes, and so it makes like a toroid. So current going in to the plane, then out. So consider this one. So both current in and out is cancelled in each turn. So current enclosed is 0. So as usual, current enclosed 0 means closed integral B dot dl is equal to 0. So magnetic field at the point Q is 0. Then finally, so what is the magnetic field inside the toroid? So inside the toroid means this one, inside the toroid. So already we know inside the solenoid magnetic field is uniform. It's similar manner inside the toroid magnetic field is uniform. So radius R1. So here radius R2. So it's radius R2, that is loop L2. So using Ampere circuital law, B dot dl closed integral, that is equal to mu 0 I enclosed. So what is the current enclosed? So current enclosed equal to number of turns. So what is the number of turns times current? So I enclosed equal to n times I. Then using, so A dot B equal to AB cos theta. So what is the angle between magnetic field and dl? That is 0. So integral dl is equal to L, we know already. So the L is the length of the loop. So L is equal to, that is circumference 2 pi R2. So theta equal to 0 here. Inside the loop, that is inside. So the current magnetic field and the line element dl both are in the same direction. So what is the angle? Theta equal to 0. So cos 0 1. So we will get B dl. So B dl, that integral dl is equal to L. So those things we have already taken. So we have already studied the previous questions. So integral dl equal to L. So L is the circumference, that is 2 pi R. Then so current I is equal to n times. So it depends upon the number of turns So B into 2 pi R2 mu 0 Ni, that is, so we are going to find what is the magnetic field inside the toroid. So the inside point is S at this point. So 2 pi R2 goes to denominator, then N divided by 2 pi R2 is, we taken as small n. Small n is the number of turns per unit length. So from this question, so we have discussed what is the magnetic field at exterior of the toroid, interior of the toroid and inside the toroid. So magnetic field present B equal to mu 0 Ni, interior of the toroid. So already we know the magnetic field is uniform inside the solenoid. In similar way, toroid also magnetic field inside the toroid is B is equal to mu 0 Ni. So okay students.